Hi, I really think you're going to like this video today. If you're familiar with the channel, you know that we do some pretty high energy videos. And I don't just mean me. The huge drone, the jet engines, the megawatt lasers, we're pretty familiar with high energy experiments. But today we're going to ramp things up a couple of notches. And so I want to reiterate the written warning disclaimer that we gave at the beginning of this video. Even though what I'm going to show you here is very easy to do, it is dangerous, and so I'm going to repeat the warning. Don't try this yourself. If you're just interested in the explosions, you can skip ahead. But what I would like to start out with is what's going on here and why this is important. We got into the idea of looking at hydrogen burning because I built a pulse detonation engine, and based on research papers, it looks like a hydrogen-oxygen fuel will be the optimal combination for a pulse detonation engine. In addition, we're building a high altitude balloon experiment, and we thought about the idea of using hydrogen as a low-cost alternative to helium as the lifting gas. After doing this research, it's pretty clear to me that the detonation engine is going to benefit from the use of hydrogen and oxygen. But the use of flammable hydrogen in a large lifting bag or a large weather balloon, not so sure that is a good idea, but you can make up your own mind after you see the video. What basically is going on when we are making explosives or we're talking about explosives is we're looking at two primary categories. One is the decomposition type of explosives. Examples of that would be, say, TNT, trinitrotoluene, RDX, one of my favorites, which is glycol trinitrate, and uranium-235. This type of reaction occurs when a particle or a molecule that's relatively stable will, when triggered, will decompose or reconfigure to reaction products that are even more stable, and in the process gives up a lot of heat. The other category of explosive is a burning type, combustion type of explosive, and that is, say, gasoline in your engine, or say dust in a grain silo, dust air burning, hydrogen and oxygen burning, and deuterium and tritium in a fusion reactor. Now, sticking with just the chemical reactions for today, the process of the decomposition is an intramolecular process. It tends to be very fast, and typically you have reaction speeds that are in the range of about 6 to 8 kilometers per second. The burning type of reaction is sort of two-stage. You have to get these moderately stable precursors together. Then they have to react to form a more stable reaction product, and so it tends to be slower. Typical burn velocities in that category are in the 2 to 2.5 kilometer per second range, with the one exception of hydrogen and oxygen. Properly mixed, or in an optimal mixture, you can achieve speeds as much as 4 kilometers per second. It is the fastest burning type of reaction you can get, other than hydrogen and fluorine, and you don't want to work with fluorine. Now, basically what happens when we are burning hydrogen and oxygen is that hydrogen and oxygen don't exist in the atmosphere as single atoms. Hydrogen exists as a diatomic molecule, H bonded to H. Oxygen, similarly, is a diatomic molecule, oxygen and oxygen. And at room temperature, even though these molecules can be in the same volume, same container, they don't burn, because this bond here is called a covalent bond. It means that essentially the electrons are being shared by the two partners, and it's reasonably stable. The same thing holds for the oxygen, and so even if they approach each other inside of a volume of gas, essentially these bonds are stable enough that the two partners are not able to exchange partners in order to form the reaction product, which is, as I'm sure you know, H2O, which can be drawn like this. Now, this bond, however, is temperature dependent. Essentially what's happening at anything above absolute zero is this bond is vibrating. There's an intramolecular vibration, a thermal vibration. The hotter you get the gas, the more vigorous this vibrates. And effectively, if you got this hot enough, the particles would actually dissociate. So the bond weakens as the temperature rises. In addition, as these particles are bouncing into each other, the hotter you get the mixture, the more vigorously they're bouncing into each other and the more they distort their electron clouds. And so you can draw this in sort of a modification of what's called an energy diagram. And effectively, what this is representing is that unless you can get these bonds to convert, unless you can add enough energy so that these bonds begin to stretch and become weak enough, and unless you can careen them into each other hard enough, they won't react. You have to get over this energy barrier. But if you reach the ignition temperature, which is sufficiently weakening the bonds and increasing the kinetic energy of the interactions, you can then cause these to form more stable bonds and in the process give up a lot of energy. It takes a lot of energy to disassociate water into hydrogen and oxygen, and you get a lot of energy when you form the water. So it's easy to make, hard to break. Now, the heat that's given off by this process is expressed in both thermal radiation. Actually, photons are being emitted by this radiation heat. But most of it is actually retained in the water molecule as extremely vigorous vibrations of the HO bond. It's actually so hot that some of these will actually dissociate. But the point is, this is vibrating very, very vigorously. And so what happens is if you get, say, a little lowly oxygen molecule here, that's sort of meandering around and eventually gets to this point here, it can pick up some of that vibrational energy, heat the oxygen molecule, and also send it careening out at a very, very high velocity where it may just run into another potential partner and begin this reaction all over again. This process will progress from the ignition point outward in what's called a flame front. Now, if you have a terrible mixture, say you've got tons of extra hydrogen or tons of extra oxygen, or you have a parasitic buffer gas like atmospheric nitrogen, it will interfere with this transfer of this energy that's being absorbed by the oxygen, and it will cause some of that energy to be lost to the parasitic gases, to be radiated out into the unreacted material outside of the flame front. Now, this is hopefully what happens in your car engine, because this heat that's distributed from the reaction zone will spread out isotropically. That means evenly in all directions. And as the burn progresses, the temperature inside the volume will slowly increase. Eventually, when it's all burnt, you'll reach an equilibrium temperature, and then everything will begin to cool down. However, if you have an optimal mixture of these two components and no parasitic gases, there's nothing to interfere with this transfer of energy, this movement of the energy to new potential reaction products. And this reaction occurs, or this transfer of energy occurs supersonically. Just like light is the speed limit in space-time at which information or effect can be transmitted from one point to another, the analogy in matter is the speed of sound. It is the limit at which elastic collisions can transmit energy or an effect throughout the medium. And when the reaction is occurring at above the speed of sound, effectively all of the reaction products around the flame front, outside, not yet involved, are not affected by that process. None of the heat is distributed to it. So none of the other gases warm, the pressure doesn't go up, the volume doesn't expand, and none of the energy is being distributed to the rest of these gases. As a result, they're just sitting fat and happy, unaware of the devastation that's headed toward them. As a consequence, all of the energy is concentrated in this very thin flame front that's moving out supersonically away from the reaction zone. And when I say thin, I mean thin, like microns thick. And because that concentrated energy is in that thin sheet of expanding gases, the pressures and the temperatures are an order of magnitude, meaning a factor of 10, higher than they will eventually reach when all of this gas is burned and you reach equilibrium maximum temperature. In addition, unlike the isotropic expansion and heating in a gas volume, shock waves tend to be directional. And so they not only will move away from the initiation point in a favored direction, but they can actually reflect off of the inside of a container. They can even reflect off of pressure variations within the gas. So you not only get a concentration of the energy in time because it's so thin, but you can get a concentration in location because the shock waves can focus. So you can reach orders of magnitude, hundreds of times, the peak pressure that you would equilibrium reach when the full burning occurs at the point of contact with a shock wave. And that's how it can cut through steel, and that's how it can shatter concrete. Now, if you're going to try to burn this as efficiently as possible, use up all of the potential energy, what you want is what's called a stoichiometric mix. And that's a chemistry term for sort of the perfect blend of hydrogen and oxygen, so that when the reaction is complete, you've used up all the oxygen, you don't have any hydrogen left over, everything has been consumed. And the way you determine what that golden ratio is you balance the equation. Now in chemistry, balancing an equation can be a real headache if you've got a very complex reaction. But in this case, it's actually a very simple thing to do, and it's kind of interesting to see how this works. Now the typical way of writing this is we have a diatomic molecule, so we have H2, and similarly we have a diatomic molecule, we have O2. In order to balance this, we can see that we have to use at least 2 oxygens. So therefore, we need to make at least 2 waters. But in that case, we then have 2 times 2 hydrogens, or 4 hydrogens required on this side. So therefore, we do this, and voila, we've balanced the equation. And what this means is we need 2 hydrogen molecules for every oxygen molecule, or at standard temperature and pressure, room temperature and atmospheric pressure. That means we need twice the volume of hydrogen as oxygen. So a cubic meter of this would require 2 cubic meters of this. Now, if you want to dig a little deeper down the rabbit hole, there's another principle called cross-section or reaction dynamics. And it turns out that because these particles are vastly different in their mass, the oxygen is 16 times heavier than the hydrogen and tends to be a large molecule moving at about 300 meters per second at room temperature. The hydrogen is a very small molecule. That's why it leaks out of balloons. And it's traveling at about 1,200 meters per second. So if what we do is we use a combination that's actually a little rich, we're going to waste a little hydrogen, and we use 3 parts of hydrogen to 1 part of oxygen, we will get an increase in the detonation velocity. And it's probably because the hydrogen is carrying away the energy more quickly because it's so light. But we can reach 4,000 meters per second with an optimal mixture, and that's what we're going to be using for our experiments. Now, another kind of nice thing about working with hydrogen and oxygen as an explosive is it's non-toxic. The hydrogen and the oxygen aren't toxic. The water certainly isn't toxic. Most decomposition type of explosives are very toxic. They're poisonous. For example, nitroglycerin is a powerful drug. Less than 1 milligram absorbed into your system is a potent vasodilator. It actually relaxes the smooth muscles inside of blood vessels. And that's why people who get angina, chest pain, related to a relative low flow of blood in the heart can relieve that by taking less than 1 milligram of that material, that drug, and ingesting it. It will dilate some of the secondary blood vessels in the heart, improve blood flow, and the cramp goes away. What's significant, though, is if you try to fabricate or you try to synthesize nitroglycerin, you will get a cracking headache because it does the same thing to the small blood vessels in your brain, increasing intracranial pressure. Finally, oxygen and hydrogen is a rather diffuse, low-density gas mixture, and so you can work with it a little bit more safely than you can with any high explosive, because even a very small quantity of that will blow a hole in your bench and send shrapnel every place. So, with that in mind, let's go ahead and mess around with it. Okay, so what we have here is a plastic container with some bubble juice in it. This is a slight modification of the formula that Nighthawk and Light gave on his channel describing the enormous bubbles that he makes and the formula that he uses. We'll go through the modification when we do the video on the big bubble machine that's going to be coming up in the near future. But in any case, what we're going to do is we're going to use this bubble juice to make some bubbles using different gas mixtures, and then we're going to ignite them. Now, the first mixture I'm going to show you is just pure hydrogen in the red balloon for the H. Balmer line for you astronomers and spectroscopists. And got a little valve. I'm going to open the valve and we're going to form some bubbles in here. Because my cameraman did not volunteer for this, I'm going to do this. I'm going to moisten up my hands a little bit, and I'm going to grab a lump of bubbles, and we're going to ignite this. Cool, huh? Let me see if I got a little bit more. I can do it again here. Okay, kind of neat. Now what we're going to do is we're going to use the oxygen and the hydrogen mixture. And this is a different animal. So we're going to use some safety equipment in this case. And one thing you'll notice is that I'm not going to use my gloves. Even though I'm wearing the hearing protection and the eye protection, I don't need that. All right. And for you headphone wearers, this is a warning. This is going to be loud, so you might want to turn things down. All right, here we go. Whoa. Different animal, right? Now, there is an there is an unexpected side effect from doing this, and that is you can't do this without smiling. It's hilarious. And what was funny is about 10 days ago, I was messing around out here, blowing up bubbles and jumping around and having a ball. And so I wanted to show my family. So I invited my wife out here and my kids, and they were looking at this, and we were blowing up bubbles and smiling and laughing and having a ball. And then I hear a knock on the door back there. And so I thought, uh-oh, the neighbors. So I opened up the door, and it's a delivery guy. I think he was from FedEx or UPS. He was a new guy. I didn't recognize him. And he went ahead, and he looked at me, and he said, "Aren't you that guy on YouTube?" And I'm like, well, yeah. And it's not implausible. His channel has gotten big enough that I have been recognized by a few strangers. But he said, "I really like that video that you did on chocolate a couple of months ago." And I said, "Oh yeah, really? Because, you know, I still got the chocolate up there. You know, we got some left over." And he said, "Yeah, I really like that video. It was really good." And I said, "Would you like to see an explosion?" And he's like, And I said, "Nah, it'll be all right." So I go ahead and I give him a pair of headphones, put it on, and I did the explosion in front of him. And he jumps back and he's like smiling like this. And I said, "Would you like me to do it again?" And I went ahead and he's like, "Yeah." So I did it again and he's grinning like a little kid. And I think the reason you have to laugh when you do this is because it's kind of the goofy combination of goofy bubbles and the devastating power of the explosion. You just don't expect it. Seriously though, the reason this is important is because pulse detonation engines are at the forefront of research in both jet engines and rocket engines, because the fact is the shock wave is such an efficient way of converting the chemical energy into directional kinetic energy that even the highest performance military jet engine on afterburner might approach exhaust velocities on the order of almost Mach 3. But when I detonate these little bitty bubbles, the shock wave and the gas is rocketing away from my hand at over Mach 9. And that's why I wanted to bring up the point about the gloves, is that when I did this second reaction, it hurts a little bit, but it's like getting slapped with a ruler. It's not warm. In the first case, I needed the gloves because it's kind of hot. But because all of the energy is being carried away by the shock wave, there's very little heat left over. And that's what makes this such an efficient thrust source, because you're not exhausting an incandescent gas. It's more like a laser. It's almost coherent. It's a directional kinetic energy that occurs when the reaction happens. And the only real problem with building these pulse detonation engines, beside achieving just the right mixtures, is because it is so powerful that effectively it tears the equipment apart. So if we're going to get into bigger explosions, we're going to need to go outside. Okay, so this is the test stand that we built in order to blow up some balloons. And I commandeered one of my son's antenna tripods as a support, and I fabricated this apparatus to detonate the balloons. If you look, you'll see that there's a red hydrogen line going in this side, an oxygen line coming in here. And that both of them go into this T-piece, which runs through two check valves, one for each line, that prevents retrograde filling of one gas into the other line so that we don't contaminate the supply lines. Typical industrial check valves won't operate at the low pressures that the balloon will create. And so we're actually using aquarium check valves, which work very well to prevent retrograde flow. The T-piece is then attached to a Yorlock fitting that has a 6mm or 1/4 inch diameter stainless steel tube that goes from this point here, about 1 yard or 1 meter up here, and exits at the end right up here. Then surrounding that is a larger diameter nylon electrical insulating tube that goes from here all the way up and not quite to that same point. And then finally there's an aluminum fitting here that has a larger diameter aluminum tube that goes around the nylon tube and again gets nearly to the top. There's a small piece of silicone tubing that acts as a seal gasket, so the only way for gas to get in and out is through the port up here. And then finally there's a piece of aluminized tape that's attached over the gasket so that we end up with a discharge spark that's going to occur between the tape and this inner tube. You can see that we have a high voltage line hooked up here and a grounding line that's hooked up here so that we can create the spark up here. These very long wires then proceed to go about 30 feet away so that I can get far away from this. And at that point I have a high voltage power supply that produces about a 40,000 volt, 1 kilohertz frequency microsecond pulse train that produces a very hot spark to initiate the explosion up here. You'll also notice that there is a third fill tube here that fills a gap between the outside of the nylon insulator tube and the inside of this larger diameter nylon grounding tube. And there is a small port located here that allows gas to flow here, between here and this point, and we'll get to that a little bit later. Now you'll see the sign below there is a bit of an inside joke. And if you're interested, you can look it up. But if you want a hint, look at Princeton University, and if you want another hint, look up Ivy Mike. And when you get the answer, you'll know what title we had considered using as an alternative to the one that we ended up with. In any case, what I'm going to do is I'm going to attach a balloon up here with pure hydrogen, and we're going to use that as a baseline. Okay, so I've just filled this with pure hydrogen, and I'm going to show you that when I use the spark, this doesn't work. The reason is there's no oxygen in there. So I have to detonate this or explode this with an external flame, just like the bubbles inside. Ready? 3, 2, 1. Pretty cool, huh? Now what we're going to do is we're going to do the same thing, but an oxygen-hydrogen mixture. Okay, so what we're going to do is I'm going to use these rings as ways of measuring the volume so I can get the 3-to-1 ratio. One ring is about 50% larger than the other, and using the equation 4/3 pi r cubed for the volume of a sphere. If we use the smaller ring and we fill with oxygen, we'll know when we have 1 part of oxygen. So my cameraman's going to turn on the oxygen and begin filling the balloon with just pure oxygen to start. Almost. Good. And then he's going to fill it with hydrogen. Good. Okay. Now in this case, it's going to be a lot louder. So I'm going to put on the headphones, and again, for you headphone users, we're going to go ahead and give you a warning here. Pretty cool, huh? From just this tiny little balloon. Now you'll see some videos on YouTube where some chemistry professors will fill up a balloon with some oxygen and some hydrogen, tie it to a string, and ignite it with a candle at the front of a chemistry class, trying to get the semester chemistry students interested in chemistry through explosions. Difference here is that because we're using an optimal mixture, not the typical stoichiometric mixture, this is a much more brisient or rapid explosion. Furthermore, because we are igniting this from the center of the balloon with an extremely hot spark, instead of the explosion having to travel across the whole distance of the balloon with an external flame, we're detonating and producing an exploding shell that is moving outward from the center. So essentially the balloon is blowing up about 3 times faster than it would typically do in one of these other demonstrations. So that's what makes this a much more powerful demonstration, because of the fact that we're optimizing the way the explosion occurs and the direction that the shock wave is traveling. But from this tiny little balloon, we got a pretty impressive result. Nevertheless, I bet I know what you're thinking. Am I right? Let's try it.
It didn't break the camera.
How can you not smile? Ah. Okay, we just managed to blow all the snow off of our roof, and it's a pretty good reverb. Now, as you might guess, we're not going to go any bigger than this. We're not going to fill a weather balloon with this. It's just too much. In addition, for safety, once we filled this balloon up, what we did is we confirmed the size, and then we disconnected the lines to the supply tanks just in case the check valves weren't working. We didn't want any chance that we would retrograde, send a detonation back up the line. But an interesting application of this is that about 60, 70 years ago, during World War II, in that era, they didn't have very sophisticated electronics, very lightweight electronics, capacitors, and flash lamps. And so for reconnaissance purposes, they needed a very powerful and compact, lightweight light source. And so what they developed was called an argon BOMB, YouTube, or argon candle, or argon flash. And basically what happened is they took a very powerful, small, high explosive and placed it inside of a larger cylinder in which they injected some argon gas, so that what would happen is that the detonation wave, as it progressed through the gas, would compress it, heat it, and it would glow. It would glow at a tremendously bright level of light, because the argon, unlike nitrogen, oxygen, hydrogen, is a noble gas and does not have intramolecular vibrations to eat up some of the energy. So it has a very low specific heat. So when the shock wave heated it, it reached very high temperatures and would produce light all the way from the deep UV into the visible. By exploding this thing below low-flying airplanes, you could actually illuminate large fields for doing photography back at the time when electronics would have been pretty inconvenient to carry on board a lightweight aircraft. So what we're going to do is we're going to wait a little bit of time until it gets darker out. And then we're going to fill again one of these balloons. But in addition to placing the hydrogen and oxygen in there, we're going to place a second balloon on top of there, and it's going to stretch over that side port that I was talking about. And we're going to fill it with a thin layer, an additional layer around the inner balloon of pure argon. And so when the shock wave exits the inner balloon, it will compress that argon and produce a very bright light. So we're going to wait till it gets dark. We're going to fill up the double balloons, and we're going to repeat this experiment one more time. And we'll see how bright a light we can make. 5, 4, 3, 2, 1. Let's bring everything in close soon, so if the cops come, there's nothing here. Let's just like throw it in quick. So, aside from messing around and once again annoying our neighbors, there are some interesting applications where a hydrogen-oxygen explosive could be useful. And one of them is the ability to disarm an explosive mixture. You know, when you light a firecracker, 4th of July, you're going to set off a firecracker and it goes off. You light the fuse, you run away from it, no big deal. But when it fails to go off, you know, you wait a little while, then you go over there and you kick it and maybe pour a little water on it. But what do you do if you've got a really large explosive? At what point would you ever feel safe to approach it again? Well, one of the interesting things that we're building is a shaped charge using a metal liner that is placed in the end of a pressure vessel that we can fill up to 20 atmospheres with a hydrogen-oxygen mixture. We're going to hopefully produce a concentrated jet of supersonic material that can potentially drill through large distances, drill large distances through armor plate or steel or concrete. But importantly, although we're using the same check valve technology that we use to fill the balloons, we are also going to add a solenoid that will allow us to dump the gas mixture if for whatever reason it doesn't go off or we decide that we want to disarm it. One of the nice things about an explosive like a hydrogen and oxygen explosive is that you can disarm it. Now these huge containers will have several 100,000 foot-pounds of energy available. And unlike, say, a balloon, which is just throwing supersonic balloon fragments around, this is far more dangerous. And so if we're going to be detonating something like this, what we're going to do is we're going to dig a trench, we're going to build a bunker so that anything that explodes is going to be kept underground and safe. And we really can't do this in this kind of weather, so we're going to have to wait a little bit of time before we get to that video. But hopefully what we've shown you already is pretty interesting and kind of exciting and a lot of fun and makes a lot of people smile. If you like what we're doing, please subscribe to the channel, hit the bell, give us a comment. I read them all, and if you have questions, I try to answer as many as I can. And that interaction really helps to build the channel, because what's happened over the last few years, since about 2016, is YouTube has redirected people away from their original content creators. They're trying to become a Netflix or an Apple TV. And so what made YouTube was original content by YouTubers. And after about 2016, if you hadn't grown your channel large, It's almost impossible to do so now if you're dependent only on YouTube's promotion. So the biggest thing that you could do for us is to share the videos. Whatever you do to sort of direct people toward the channel will help us to grow, and the bigger we get, the more we can afford to do, because as you can guess, what we do here, although it's a lot of fun, it costs a lot of money and it takes a lot of time. And by promoting this and helping us to grow, we can do even more, and we can produce more videos more frequently. In any case, I want to thank you very much for watching. I wish you a very good evening. Stay safe and take care.